So I think what's going to work out best here is just to go ahead and do some of the examples in the videos, and then in class we'll talk about more of the details. Okay, so here we are in 9A page 2, 9A packet page 2. We're just going to do the examples. And in talking about, for example, 4, we want to know if this series converges or diverges. If it converges, give its sum. So the only series that we've really studied so far have been geometric series, and so that's what we're going to go off of. In fact, this is a geometric series, and if you can't tell it's a geometric series, the most important thing to do is just to go ahead and write out the first few terms. Okay, so we know how to do this. When n is 1, we replace n with 1, and then we get 5 times 1/2 to the 0 power, okay, by replacing n with 1. And then we're going to replace n with 2, and we get 5 times 1/2 to the first power, and then plus 5 times 1/2 to the second power, and so on. So this goes on to infinity, so we have an infinite series, and if you notice, we've got from the first term to the second term. Let's actually clean this up just a little bit. So we have 5 plus 5 times 1/2. We can make that 5/2 plus 5 times 1/4. Okay, plus dot dot dot. As you can see, what you're doing here is you're multiplying each term by 1/2 to get to the next term. And as we talked about in class, that number inside the set of parentheses that's being raised to a power is going to be our r. So once we find the r, we also know our first term. So we have a is our first term. And we know from what we've already done, like I said, that the sum of an infinite geometric series is the first term divided by 1 minus the common ratio. Okay, as provided that that common ratio, the absolute value of it, is less than 1. Okay, so we can see that we have r, which is 1/2, and we know that the absolute value of 1/2 is 1/2, and that's less than 1. And we have so that checks out. We are allowed to use it. So we're allowed to use this formula to find the sum of this infinite series. So let's go ahead and put our first term up on top, divided by 1 minus our common ratio again, which is 1/2, which is 5 divided by 1 minus 1/2 is 1/2, and 5 divided by 1/2 is 5 times 2 over 1, which is 10. I urge you to not try to do too much in your head. There's a lot to think about in this unit. So there you go. We have the sum of that series is 10. All right. So let's make sure we answer the question, though. Does this series converge or diverge? It converges. So you can circle that. If it converges, give its sum. So we did all that. So we answered our question. All right. So the next one, maybe we can get a little trickier here. We already know that when that number inside the set of parentheses is being raised to the power that's changing, we know we have a geometric series. So we know that the absolute value of 2 over 3 is 2 over 3. That is less than 1. Always just go through this process. Just go through it. You go, okay, got a geometric series. But what in fact is our first term? So let's write out our first term. When you replace k with 0, you get 2/3 raised to the 0 plus dot dot dot, which is 1, plus 2/3 to the 1, so we could write 2/3, 2/3 to the second power, which would be 4/9, and so on. But we already had our r, and so all we needed was our first term, so that's our a, and therefore we have our sum equaling the first term, which is 1, divided by 1 minus our r, which is 2/3, which is 1 divided by, now I do, even though I can kind of see it here, I can do this in my head, I don't want to leave it to chance. I want to make sure I write everything down, because on a test, whatever, you're going to be thinking about a lot of things, and so just write it down. Okay, 1 minus 2/3 is 1/3. Okay, 1 divided by 1/3 is 1 times 3 is 3. So you can kind of guarantee yourself of not making any mistakes as long as you do these things. So again, circle the word converge. Yes, it does converge because we get a finite sum. Okay? Well, let's look at the next one. We're not given our sigma notation, so we can handle that. We can see our first term is pi over 3. That's our first term, A. And then how do we get from one term to the next? Well, if we look here, we can see we're going to multiply pi by pi to get pi squared, and 3 by 3 to get 9. Let's see if that works. Okay, so we're going to multiply the first term by pi over 3 to get the second term. Are we going to use the same numbers? So let's see. If we multiply pi squared over 9 times pi over 3, we get pi squared times pi is pi cubed. 9 times 3 is 27. So in fact, our value for our common ratio is pi over 3, but we want to make sure pi over 3 is less than 1, or the absolute value. Well, we know that pi is a little bit bigger than 3, so that's actually going to be bigger than 1. So we say, therefore, the series, we can just refer to this as the series. It's the only series we're concerned about in this problem. The series diverges. And if this were an FRQ, you'd want to make sure you state this. You have to have some reason why the series diverges. You would say that, and it is a geometric series. You have to state that. It's a geometric series with R, the absolute value of R, is greater than 1. And so that's why it would diverge. Okay? Well, that's it for that page.